We had left off talking about bonds that can form when elements are going to join together. We left off talking about the polar covalent bond, and we gave the really good example of water, because water is a substance that we definitely have to have for life, okay? And the properties make it, it's the only substance on the planet that is going to exist in all three states. We kind of used that information about water, and then I think, did I use sodium chloride as an example to form the ions? Okay, so we're going to continue talking about that. And when we begin to look at ions, there is a reason why they are so important. Can you remember what we talked about on Tuesday as to why ions are so important? They carry an electrical charge, so they have the ability to generate electricity. Now, you're probably thinking, electricity in the body? Yes. How do I know that electricity exists in the body? Okay, nerves are going to be one of the cell types that are, that have the ability to generate a potential. Now, how do I know that nerves can do that?
Action potentials.
Well, that's what they can, we know they can do that, but how do I know that they can do that? By just doing something to the human body to check it. How can I check this electrical potential of the nerve cells?
Touching something?
Well,
Feeling something?
okay, think about this for a second. Ever gone and had all those little sticky things stuck all over you? Okay, all right, it's called an EEG, electroencephalogram, okay? And that's for the brain, which is nerve tissue, okay? And they put the little sticky things all over you. You're hooked up to a machine. They turn it on, and it gives them a little readout on a piece of paper. What is the readout? How did that get created?
These electrical impulses in the brain?
It's from the electrical impulses that got created. Can the same thing be done for the heart?
Yes.
Can the same thing be done for the muscles? Yes. Now are you getting the reason why I need you to focus on these charged particles, these electrons? How would you be able to know in a clinical setting that these may be in or imbalanced? Blood work. And if somebody is being sent for blood work, I'm guessing they think something is wrong. Correct? Now, think about this. What level am I trying to get you to think at?
Cellular.
The cellular level. Haven't even gotten to the cell yet. And I'm trying to get you guys to begin to think in that direction. Okay? Because that's going to be the basis of everything. So when we look at these ions, calcium, sodium, potassium, hydrogen, hydroxides, chlorides, bicarbonates, ammoniums, phosphates, irons, magnesiums, iodides, these are going to be, some of them, in very trace amounts. But their importance cannot be stressed enough. All of these little charged particles are going to have a very important part to play in your body. When we take two or more atoms, elements, atoms, okay, and if they combine, we're going to create a molecule. For example, hydrogen. When we look at the periodic table, some of those elements, those atoms, okay, they exist in a gaseous form. And they exist in what we call diatomic form. Di meaning two, atomic referring to that particular element, okay? Because think about this for a second. Oxygen, it's a gas, but how do you always see it written? O2. Because an oxygen will bind readily with another oxygen. Hydrogen will bind readily with another hydrogen. Fluorine to fluorine, for example. A lot of our gases exist in a diatomic form. When we have two or more that will chemically combine and give us an independent unit, such as the diatomic gases, we will have a molecule. When we get something of different types of atoms, if we get two or more, we get a compound. Good example, water. I've got hydrogen and I've got oxygen. They do chemically combine and it gives us a compound. CH4, methane gas. Carbon, hydrogen, they chemically combine and I get methane gas. We can take the combinations of these materials and we can get their molecular mass. Am I really concerned about a lot of that? No. Okay, but it is a part of chemistry. Now, we simply take their atomic numbers, add them together based on how many we have. For example, H2O. I have how many oxygens? But I've got how many hydrogens? Down here for sodium chloride, how many sodiums do I have? How many sodiums do I have? One. I have one chlorine. That's not exactly the proper right way, but for our purposes, if you add the two atomic masses, you've got the molecular mass. Now, that information definitely becomes important because when you begin to do a lot of chemical reactions and so forth, these are some numbers you have to keep up with. For our purposes, it just lets us know the weight, okay? The weight of that particularly combined molecule or compound. When we get the combining, let me say the chemical combining that goes together. This gives us intermolecular forces. For example, H2O together, it has an intermolecular force. That attraction between those elements. When we talk about bonding that occurs, we have bonds that form that will be considered weak. We'll have bonds that are going to form that are considered strong. And believe it or not, we're going to have bonds that form that will be weak but very strong. I know, just doesn't sound right, does it? The bond that forms that is weak but extremely strong is hydrogen bonding. Now let me tell you what I mean by hydrogen bonding. What molecule are they showing right there? Water. They're showing me my great big oxygen, my two smaller hydrogens. Do you guys remember how I said that because a lot of the electrons will exist around the oxygen, it has a slightly negative charge, this electronegativity? And then the hydrogens, because they don't have as many electrons, it's more positive and opposites attract, okay? This is how this connection is going to be made. The oxygen is going to be attracted to the hydrogen. The bond that forms is termed a hydrogen bond. These are going to be connections that have a little bit of a charge to them. But wait a minute. I just said hydrogen bonds are weak but strong. Think about the properties of water. The properties of water happen because these bonds do something. For example, water is the only, I'm going to say this until you get tired of hearing me say it, the only substance that exists in all three phases: solid, liquid, gas. Water as a liquid. Water. Okay? Liquid. But it's constantly breaking, forming, breaking, forming, breaking, forming, breaking, forming those hydrogen bonds. I'm going to take that water and I'm going to put it in a deep freezer. And eventually, this liquid, where the bonds are going, breaking, forming, breaking, forming, breaking, forming, breaking, forming, okay, it's going to eventually begin to harden, to it gets more hard, to more hard, and that's going to be my solid state. Guess what those bonds have done? They are no longer breaking, forming, breaking, forming, breaking, forming. They have become stable. Now, I'm going to take it out of the deep freezer, and I'm going to put it in a pot on the stove, and it's water. Watch the pot never boils. So you know that the longer you stand there and look at it, it's not going to boil. Okay? The minute you turn your back and walk away, it's going to boil. All right? What comes off?
Water vapor.
Steam. That is my gas. What happened to bonds?
Molecules got super excited.
They what? I broke the bond. However, how much energy did I have to put into those molecules to make that bond break?
I can get joules it takes for 270 pounds.
Hmm?
Joules to Fahrenheit.
All right. And you just gave me a number.
Yeah, 275.
212.
212, that's good.
Yes. 212 Fahrenheit is the amount of heat I had to put to make those bonds break. Now, that is a tremendous amount of energy. Why? And at what point does water freeze? 32 Fahrenheit, 0 Celsius. Why is this important?
Freezing point and the boiling point of water. It changes its properties.
I am roughly 75% water. Now, think about this for a second. My body's roughly 75%, my blood's roughly 75%, a cell is roughly 75%. Do I want water boiling at 100 degrees Fahrenheit? Why?
Because your body's
Because we get to temperatures around us of 100 degrees. And we would just kind of turn into vapor. Now, granted, I paid $10 to see that. Okay? Now, what about that little freezing point? Why is that important? It's got to get pretty low for the water to freeze. That applies to my body. But wait a minute.